Yeah, maybe you'll wash it off less days.
Okay, so matrix operations and matrix algebra. Many of these chapters are titled very, just like any of the chapters could have been named any of these things. So, yeah, matrix algebra. So today we're going to be talking about properties of matrices and matrix operations. And we actually today will be learning a new matrix operation. You thought you knew one? Thought you did? Apparently I have energy this morning. All right, so we already know through experience that matrix multiplication is not commutative. Commutativity is the ability to operate in any order. So matrix A times matrix B generally is not equivalent to B times A. However, we do have a whole ton of other properties of matrix operations. So matrix multiplication is associative. Associativity means you don't change the order in which the matrices are being multiplied. And order is a weird word here, meaning you don't reorder A, B, and C. It's still A, B, and C, A, B, and C, but you change the grouping. So when you actually do the operation, here you multiply B times C first, get that result, and then multiply it by C. Here, you multiply A times B first, get that result, and then multiply by C. And those results will be the same, and that's called associativity. So matrix multiplication has the associative property. You can distribute matrices given you keep the correct order. So when I take a look at this, I can left distribute matrix A, and I can right distribute matrix A. But because you don't have commutativity with matrices, these are not going to be equivalent. So the one gives you AB plus BAC, and the other gives you BA plus CA. Not the same, necessarily. That's why you need two distributive laws for matrix distribution. Then you have the ability to multiply by a scalar before multiplying, or where you are multiplying a scalar by a product of two matrices. You can either do the matrix multiplication first and then multiply in the scalar, or you can multiply one of the matrices by the scalar, get that answer, and then multiply it by the other matrix. Those are all the same thing. So that's multiplication by a scalar, meaning you can do it at any point during the operation of matrix multiplication. After the matrix multiplication, or to one of them prior to the matrix multiplication. Then we start to get into the identity property. And when you get in upper levels of math beyond this, you have to prove associativity, that the identity exists, what is the identity, scalar multiplication, things like this, to brand new operations that have not been defined in your lives so far. So that's why it's really important to know what these are and then know how to prove them. And so for let's say a 2 by 2 matrix, I2 is that 1, 0, 0, 1, for example. It's essentially a diagonal of ones. I call upper left to lower right the main diagonal, just because, I don't know, it's the one that contains the ones with the identity matrix. These will be ones, the rest will be zeros if you have an identity matrix. And what the identity matrix is, it is the one that we have in multiplication. So it is what we can multiply by and maintain the same matrix. So just like the multiplicative identity in regular multiplication is 1. In other words, if I multiply 5 times 1, I keep the 5. The additive identity in regular addition is 0. Because then when I add any number to 0, the number stays the same. 5 plus 0 is 0. This is the identity for matrix multiplication. Matrix identity multiplication must be commutative. Okay? So it has to commute, it has to work both ways. Now, if matrix A is not a square matrix, that means these might not necessarily be the same i's. Okay? So you choose whatever I you have to have in order for the multiplication to work. And remember, if you have an M by N matrix, it has to multiply by another matrix that starts with an N. If it doesn't, these two must agree. They have to be equal. Let's say N by P. These have to be equal in order to multiply together. So you have an N by N matrix times, for example, an N by P matrix, and that'll yield an M by P matrix. So when you choose your identity, it just has to be the one which provides this middle equivalence with the matrix multiplication. Questions? So this is the new operation I was telling you about. It's called transpose. So you can transpose a matrix. And a transposition of a matrix, or the definition of a transposition, is switching the rows with the columns and the columns with the rows. And it's denoted by a T, or T looks like a power, but it's really just a notation. When you transpose a matrix, because you're switching the rows with the columns, an M by N matrix becomes an N by M matrix, because the rows are switched with the columns. So therefore, unless you have a square matrix, the dimensions are going to be changed. So here, we have row 1 of this matrix is 3, 8. So for AT, column 1 is going to be 3, 8. So row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. So that is A. A was 3 by 2. Really be using the equal symbol. AT is 2 by 3 in terms of its dimensions. Any questions on how to find the transpose? So there are some properties of transpose, some of which seem obvious, some of which I think are very interesting. So if you, for the first one, transpose a matrix and then transpose it again, you get the original matrix back. It's kind of like doing a handstand and then doing another flip, like, okay, rotating your entire body 180 degrees, then rotating another 180, then you're standing and you're back out to your original position. I was going to say doing another handstand, but that's not what you would call it. You would just call it standing up. So, yep. So you write what was done to the matrix. You can distribute over transpose over addition, meaning you could add the matrices together and then take the transpose, or you could take the transpose separately and then add them. The same result occurs. Scalar multiplication works before or after you do the transpose. And these, I think, make sense when you do the operation, that it would be the only way that would occur. Now this is cool. This is the one that's forgettable, but that needs to be true. In terms of matrix multiplication, this has to be true, but it's something that I always forget that, you know, when it comes up, I'm like, oh yeah. So when you transpose a product, it is the equivalent to taking the transpose of each matrix separately, but you have to reverse the order. And when you think dimension-wise, this makes a lot of sense. Because if A and B were able to be multiplied to begin with, that means their inner dimensions had to agree. Well, if you flipped A and you flipped B around, then the dimensions flipped, okay? And if the dimensions, okay, so my thumbs are what are equal in this scenario, in my lovely using my hands to teach here. So these, when you did A times B, here's A, here's B, these had to agree. My two thumbs had to agree. But when you transpose them, this happens. Well, these don't necessarily agree. So you have to switch them, and then you have the thumbs which are equal. Okay? So, sounds correct.
I'm not surprised, but it's kind of like, I didn't see that coming.
All right. So you just have to reverse the order, but if you do this in terms of dimensions again, then it makes sense. Wow. So you can take a power of a matrix. The power of a matrix is defined just like the power of any variable or any number. It's just the result from repeated multiplication. And because we can define repeated multiplication really through a power of 0 at the lowest possible in terms of integer quantities. 0 would be the lowest possible quantity we can consider, and a to the 0 is really like the 1 in regular numbers, scalar quantities, I should say. So A0 is then the identity matrix, okay? Because if k equals 0, A0x should be x itself, and so that means A0 is the identity. Or else it wouldn't be true. Because the only thing that preserves the vector is the identity. Everything else will change it in some way. Any questions? Now, very soon we'll get to go back to algebra 2. Well, that'll be good.
Meaning no matrices?
We learned about matrices in algebra 2.
Yeah, but that was the one dark spot, glorious.
Yes, we all know. Okay. So, in algebra 2, we learned about matrix inverses. The inverse of a 2 by 2 matrix is something we focus on in particular because 3 by 3 we actually use our calculator to do, if you can recall. And the way an inverse works, and they use the word invertible, and Ray used this word before when he was looking up that theorem. Oh, I don't know why I highlighted there.
Well, it was a thing where you like flip the A and B and then you negatize the C and D or something.
And another thing, but
You flip the C and D also?
no, you have to multiply by something, a scalar quantity.
Which is the determinant. Come on.
What? It's not that.
I mean, like, I'm sure you're right. I'm just exactly what that is. Whatever the, yeah.
Okay, so Ray before talked about, or he looked up what the theorem was called with all of the A, B, C, D. I told you we keep adding. And it's called the invertible matrix theorem. And the reason why they didn't give it that name in chapter 1 is because we weren't talking about invertible matrices at that point. Now we are. An invertible matrix is a matrix that has an inverse. If you have a matrix, in this case C, that you can multiply by matrix A in either order and you get the identity, those matrices are inverses of one another. So A's inverse is C in this case. And As a reminder, the way we denote inverses is with this. It looks like a -1 power, but it's not. It's just notation for inverse. So A inverse equals C. And the inverse of C is A as well. Or I should not say as well, but that is also true. These have to be true together, or else these equations wouldn't be true.
I think you meant to put the inverse sign.
Oh, darn. Yeah, I wrote the same thing. Well, not the same thing. I wrote there. Okay. So there we go. C inverse equals A. And so that is an inverse. Now, inverse is so important because it allows us to solve equations. The whole thing of like x plus 5 equals 7, the ability to solve that equation is to add the additive inverse of 5 to both sides. Okay? So if I'm solving in algebra 1, what allows me to solve this is the fact that the additive inverse of 5 is -5. In other words, 5 has an additive inverse. So 5 has an additive inverse. The additive inverse generates the additive identity, which is 0. And the definition of identity is that this plus this preserves the x. So inverse allows us to solve equations. Identity allows us to cancel things. So C is uniquely determined by A, and this just describes why you can't have another inverse. It has a unique inverse. So A has one inverse and only one inverse in matrix multiplication. And that is if it has an inverse at all. Not all matrices are invertible. Any questions? Okay. Well, I think by Mark announcing what the inverse is, he kind of gave it away, but I was going to have you guys try and guess and check the inverse of this. We'll see if we can just erase that from our memories for a moment.
You didn't have to tell me I was right, or Wilmar was right.
Yeah, that's true. So I want to know what I can multiply that by to get 1001. Because the definition of an inverse is that a matrix times its inverse is I. So I think the cat's out of the bag. So we'll just do the operation. So what we learned about as a freshman is we learned that it was 1 over the determinant times, and it was for matrix A, B, C, D. You flip-flop the D and the A, and you negatize the B and the C.
Couldn't you, like, just set up an equation for this? Like, if we didn't know that that's what it was.
Yep. Or you could just kind of bounce around with it. Right. So here, if we flip-flop the D and the A, the 4 goes here and the 1 goes here. And then if we negatize the other one, oh my goodness, sorry guys. If we negatize the other side, we get -1, -3. And what's the determinant of that matrix? 1. So it's 1 over 1 times that.
Pretty good.
So here, we have 4 minus 3 gives us the 1, -1 plus 1 gives us the 0, 12 plus -12 gives us the 0, -3 plus 4 gives us the 1. So that is the inverse. So this is what I just wrote, but the definition of inverse, A inverse is 1 over the determinant, and the way you find the determinant is it is the difference of the two diagonals, the main diagonal, AD, minus the subsidiary diagonal, BC, over the jogging around of that. Okay?
If you have like a 3x3 matrix, is you have to like do a lot more stuff.
We get to learn how to do it this year by hand.
But we're gonna use the calculators on the test, right?
Well, not to do that.
Oh.
That's so sad.
We have to find.
Okay, so, yeah, it's a really fun, okay, by fun, slightly tedious method.
Literally everything to do with matrices is slightly tedious.
Yeah. Oh, no, this is worse.
Yeah.
And the reason why it's worse is because the fractions, that's really the long and short of it, but the determinant is kind of baked into that determinant, and so that ends up cropping up as you choose the method to do it. Okay, so the way you know that your matrix is not invertible is all centered around the determinant. Because we multiply by a scalar quantity 1 over the determinant, if the determinant ends up being 0, that means it is not invertible. So matrix A is invertible if and only if the determinant does not equal 0, and that is actually true for any square matrix, not just a 2 by 2. Questions on that? Okay.
So that's like saying if you had like a matrix that was like 4, 10, 2, 5, that would not be invertible.
Yes.
But like,
And do you see how these are multiples of one another?
and that's why,
Yeah.
because they would always be the same kind of vector.
Yeah, the equations are dependent upon one another. You have a linear dependence there.
Is that like an inclusive set or true of all? That would have,
Square matrices.
well, right, but I mean, like,
Didn't we say that it has to be a square matrix? Like an n by n matrix?
I guess
That's what it said in the previous page. For inversion, we needed an n by n matrix. Yeah.
For
Otherwise,
invertibility, they have to be the
because
same.
otherwise you couldn't move the c to other side. So it doesn't look fun.
Yeah, you wouldn't have that commutativity with it.
You can have like non.
Say that again?
I'll just do it.
If you have non, like, if you have like a 3 by 2, then you have one for like the 3 side and one for the 2 side.
You could, but it wouldn't be the inverse because inverses have to be commutative.
Oh, so
By
like, what would
definition.
you call it then?
Fun little buddy there that produces the identity matrix.
The fun little buddy.
All right, so if A is invertible, that means that this equation has a unique solution. And the solution is x equals A inverse times B. And we, Mark?
Sorry, do our calculators, like when they solve inverse matrices, do they set up like a matrix to solve for it? Like, you can usually, like, for the one that we just did.
It uses matrices, I know. Uh,
You'd have like a system of equations, which then you could solve with a matrix, which I feel like is kind of weird.
Oh, you mean like for the 3 by 3s?
Well, just, I mean, for a 2 by 2, for sure, you can do it that way. You can also do it the way that we just talked about, which is probably easier for programming, but I was wondering if the 3x3, they would do it that way. 'Cause,
Yeah, I
like,
don't know.
you could be, like, in theory, it wouldn't be, like, impossible to do it. It would actually be, like, fairly easy. You just have to program it to do that.
Right.
What's the word?
But
What's the word you're talking about?
I'm saying that, like, because in general, like, if you have to solve for a 3x3 matrix, you get, like the inverse of the 3x3 matrix. You could do it with a system of equations to just get, like, a gnarly matrix, which would be really big. But, like, in a calculator, it shouldn't matter. So that's why I'm wondering if they're using matrix to solve a matrix.
Okay, real quick, the reason why this is true is if I left multiply both sides by a inverse, and again, left multiply is a very specific term, but you have to be very clear with that. If I left multiply both sides by a inverse A becomes I. So this is Ix equals A inverse B. Ix, because of what the inverse does, is just X. So this is the algebra which proves that to be true. And we actually did this freshman year with you guys, this whole thing, and you're like, do we have to do that every time? And I said, no, you just have to know where this B equals X inverse, or A inverse B comes from. That's where it comes from. Okay, so this looks a lot like our rules for transposing. If you invert a matrix, take the inverse of a matrix, I'll say it that way. You can do it either. And then you take the inverse of that matrix, you get the first matrix back. It's kind of like adding 5, and then you subtract 5. You do the operation, you do the inverse, you get exactly what you started with. If you take the inverse of a product, you can take the inverse of each matrix individually, but again, the order changes, just like they did with the transposition.
Why does it matter?
Because AB does not equal BA. These are not inverses of one another, A and B. These are just regular matrices.
Right, but we said that before the reason they did it was because of, like, the dimensions. Here it has no, it shouldn't have anything to do with dimensions.
Well, dimensions, well, it doesn't, because everything is
The same
square.
for all the n.
So it is true. The reason I explain that with the transpose is because I feel like it's easier to remember it that way, but that's not why it is true.
Oh, okay.
Why it is true, we would have to set up a proof with, for example, 2 by 2 matrices, where we define matrix A as A, B, C, D, we define matrix B as E, F, G, H, we multiplied them together, took the inverse, and then compared it to each. And what happens is they get flipped. And this just shows that transposing and inverting can be done in either order, and you get the same results. We're going to do an actual problem.
Oh, I thought we were gonna get out of that.
So we're going to solve this using a matrix inverse. So what I'm going to do is first set up a matrix equation. My first matrix is the coefficient matrix, which are the coefficients of x's and y's. So this is called the AX equals B equation. And what we proved on the former slide was that X equals A inverse B. So what we have to do is find A inverse. Well, to find A inverse, let's find the determinant of A. The determinant A is going to be 35 plus 3. That's 38, because you have to do the subtraction of the two diagonals. And then we're going to jog it around. And there is our inverse. Any questions on that? So now I can go about solving the equation x equals A inverse B. So A inverse is 138. Okay. And one of the properties we talked about is the fact that I do not have to multiply in the 138. I can multiply the two matrices together first and then multiply in the 138, which makes my life a little easier. So when I multiply these matrices together, it is row by column. So I get 85 minus 27.
Wait, isn't that 65?
Oh, 65 minus 27.
Okay.
And then I do negative 13, negative 63. So that's the result from multiplying those together, row by column, row by column.
Wait, isn't it 36?
76.
Oh,
Otherwise, we're going to hear 75.
stop it.
It's not contrived at all then. It's the elegance of math.
Math is not the same.
Well, it's just like a system of equations. The fact that it's 138 has nothing to do with anything. It's just that system of numbers.
Any questions on that?
But like it's not.
It is.
No, the 138 has nothing to do with anything. The only thing that makes it contrived is that they're real numbers. It's just when you end up in
Come up with a random system of equations. Give me an answer where it's a matrix with numbers in the tens.
Yeah, but I know, but you guys are talking about being contrived because it's divisible by 38. But
Yeah, that's not the contrived part. The contrived part was when I wrote these equations, I knew the answer.
right. But the
So I
program-
made up the equations based on the answer instead of just coming up with random numbers so that these would be nice.
I wasn't saying it was 38. I'm saying.
All right.
That's what's
Oh, holy cow. Okay, how much different? Oh, this is so cool. Holy cow. What was I thinking?
We can do it tomorrow.
Oh, no. Shh.
Yeah, let's do it tomorrow. I don't think we have time.
We have like 4 minutes. This is like that start.
We can do a quick 9
Okay,
minute.
no, let me talk, shush. All right. So, these are called elementary matrices. Elementary rate matrix is called an elementary matrix because it is obtained from elementary row operations on I. So if we take a look, what is the difference between E1 and let's say I? Mark?
R1 and R2 are like flipped.
Yes. R1 and R2 are flipped. So what that means is if I multiply A by E1, you know what's going to happen?
R1 and R2 are going to.
It's going to flip R1 and R2. It accomplishes that row operation. That's why they're called elementary matrices, because they accomplish elementary row operations.
Wait, how does that work?
Here, let's see.
Is it when you multiply it out?
Is it? Wait, wait. All this is legalities. That doesn't matter. Doesn't that like assume that all the values are the same? No, you keep the everything. It'll defeat the after.
Well, yeah. Yeah.
Because it's an identity matrix. Except you.
So here's E times A, which is just our generic. So row times
Oh, yeah.
column.
That's
See? I know it's gonna happen, but I just wanna actually do it. See?
really care.
Whoa, it's all connected. It's so
Like,
cool.
but like, can't you just do that elementary row operation with A without multiplying E through it?
Yeah, this is 5R3 here. I think that's pretty obvious. What does this one do?
Just -4R1
Yep, -4R1 plus R3, and it's placed into R3 as it should. Remember, we talked about good elementary row operations. There's one unchanged row and it gets placed in an unchanged row. So you can accomplish every row operation by doing a matrix multiplication. This is why this is cool. If you had a series of multiplying by elementary matrices, it's just like doing a series of elementary row operations. Okay? So any matrix that's invertible, you can take from IM to what it is by doing a series of elementary row operations or multiplying by a series of elementary matrices. So if you multiplied all those elementary matrices together, that would be like the same as doing all those elementary row operations. Okay? So, like, let's say you wanted to get this matrix and you wanted to get it to be I because you wanted to solve. Let's say you didn't want the pivot columns, you wanted the whole enchilada.
Cool.
Okay? You wanted to get it to look like this. So instead of doing all of those elementary row operations, you could just multiply by the product of all of those matrices, all of those elementary matrices, which represent all of the elementary row operations. So this is E, all the elementary matrices, but all of them. What would E be then?
The inverse.
This is the inverse.
Oh.
So in other words, doing this series of elementary row operations to get to something that is solvable is basically generating the inverse if you think of it in terms of elementary matrices instead of elementary row operations. So each elementary matrix is invertible. The inverse of E is the elementary matrix of the same type that transforms E back into I. In other words, if I had that matrix that flipped 1, row 1 to row 2, the inverse of that would flip row 2 to row 1. So those are inverses. So that's how you do an inverse of any matrix, is you consider undoing all of the row operations in matrix form. Okay, yeah, that's that. There we go.